Let us look at standard integrals. What are they? In integral calculus, certain integrals occur so often that the results are memorized as standard integrals. So, since these integrals very frequently occur, we need to remember this. So, let's take it one by one. Integral of c times f of x dx equal to c times integral of f of x dx. So given a function f of x, let us scale it by a factor c. So let's say f of x is this and c times f of x is this. This could be scaled in any manner. By the way, this straight line is because we are multiplying it by 0. Then the rectangles in the Riemann sum will also scale. So area of x is approximately equal to the Riemann sum. K equal to 1 to n summation of c times f of x k minus 1 delta x. Now let's take it step by step. A of x is approximately equal to, now when we do summation, if all the elements of the summation, all the terms of the summation have a common factor, we can take it out. So we have taken it out. So c times the Riemann sum of f of x sub k minus 1 times delta x. Now remember, we take the limit of the Riemann sum, so which becomes c times the limit as n goes to infinity of the Riemann sum, and that is the integral. So the moment we take the limit, it becomes equal to limit as n goes to infinity. Till that time, it is an approximation. So, which is what we had to show. We started off with c times f of x dx integral, and we ended up with c times integral f of x dx. Now, let's look at the second one. Yes, now this is really, really important one. Integral of x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1 plus c, where n is not equal to minus 1. So how did we arrive at this? We are not going to look at that. We can, derive it from first principles, that is, using the Riemann sum. But what we'll do is we will prove that this is correct. How? By taking the derivative of this. When we take the derivative of this, we should end up with x to the power of n. So let's do that. So let's say capital F of x equal to x to the power of n plus 1 by n plus 1 plus c. Let's take the derivative. Capital F prime of x equal to, now 1 by n plus 1 is a constant, so we can take it out, times the limit as h goes to 0 of x plus h to the power of n plus 1 minus x to the power of n plus 1, the whole thing divided by h. Now we expand this term. The idea is that we have to start off by expanding this, and once we have expanded it, we try to arrive at this itself by subtracting this from the expansion and dividing the whole thing by h. So we use the binomial theorem. So x plus h to the power of n plus 1 is equal to x to the power of n plus 1 plus, remember combination, so n plus 1, 1 x to the power of n h plus n plus 1, 2 x to the power of n minus 1 h square plus n plus 1, 3 x to the power of n minus 2 times h to the power of 3 and so on till we end up with h to the power of n plus 1. So basically what this is doing is, it is, these in brackets are providing us the coefficients of the various terms in the expansion. Okay. This is also written, remember, as n plus 1 C1, n plus 1 C2, n plus 1 C3. And here it is not mentioned. Actually, I should have mentioned it. It should be n plus 1 C0 or n plus 1 0. Here again, I should have mentioned it n plus 1 n plus 1. But in both these two cases, it will end up as 1. So that is why it is not mentioned. Okay, anyhow. Now subtract x to the power of n plus 1 from both sides. What do we get? X to the minus x to the power of n plus 1. And from the right hand side, this x to the power of n plus 1 disappears. Now when we evaluate this combination, we end up with n plus 1 times x to the power of n h. Plus, we leave these as it is. Now we divide by h. See, by subtracting this term, we are getting the numerator. By dividing by h, we are getting the complete expression. So when we divide by h, what happens here? This h disappears. From h square, 1h disappears. From h cube, 1h disappears. And from this, 1h disappears. So that we are left with x plus h to the power of n plus 1 minus x to the power of n plus 1, the whole thing divided by h. And on this side, h disappears here. And the rest of the, from each of the rest of the terms, 1h disappears. Taking the limit, h goes to 0. So limit at s goes to 0 of x plus h to the power of n plus 1 minus x to the power of n plus 1 by h is equal to the limit of the whole thing. We actually take the limit in the right hand side by doing direct substitution. So here what will happen? This h is 0, so this whole term disappears. H, whole term disappears. So except the first one, all the terms disappear. So we are left with n plus 1 x to the power of n. Okay. Now what does the left hand expression signify? The LHS is the derivative of x to the power of n plus 1. So we can say f prime of x is equal to 1 by n plus 1 times the limit h goes to 0 of this term is equal to n plus 1 x to the power of n divided by n plus 1. Now here remember 1 by n plus 1 and n plus 1 x to the power of n. N plus 1 cancels out and we are left with x to the power of n. Now by definition, an antiderivative satisfies f prime of x equal to the function f of x. So which means capital F of x, which is the integral of x to the power of n dx, is equal to x to the power of n plus 1 by n plus 1 plus c. And f prime of x equal to f of x, which is equal to x to the power of n. So therefore, integral of x to the power of n dx is equal to x to the power of n plus 1 by n plus 1 plus c, where n is not equal to minus. Here we are looking at now the integral of 1 by x dx. Now, remember this in the previous one, n was not equal to minus 1. But if we take it as minus 1, this becomes 1 by x. If we take n as minus 1. So, which is what we are going to do. And its integral is natural log of absolute value of x plus c, where x is not equal to 0. Now, in some cases, immediately we know the derivative of the RHS. You know, the derivative of natural log of x is 1 by x. And c, of course, disappears. But here we have to be careful. For x greater than 0, natural log x is defined and differentiates to 1 by x. For x less than 0, we take the opposite of this statement. That is, minus x is greater than 0. So in this case also, natural log of minus x is defined. Basically, these are the graphs. This is our natural log of x, and this is natural log of minus x. Let's take a point A on natural log of x and a point on natural log of minus x for the same value of x as b. And let's draw the tangents, which is what the derivative gives us, the slope of the tangent. So here, as I move A, B also moves accordingly. And in both cases, the slope at A and B are the same. The only difference is the sign. In this case, it is positive. In this case, is negative. So here we have a positive slope. Here we have a negative slope. But the numeric value of the slope itself is equal. Derivative of natural log of minus x is equal to 1 by minus x times the derivative of minus x, which is minus 1, which is equal to 1 by x. So since in both the cases, the derivative is same, but remember here, x is negative. So which means the sign will be different. So here the sign will be minus. Here sign is plus. But the values remain the same. So since in both cases the derivative is the same, or I should say the magnitude of the derivative is same, we combine both and take the absolute value of x. So since in 1 by x, cannot be equal to 0, therefore integral of 1 by x dx equal to natural log of magnitude of x plus c, where x is not equal to 0. Okay. Fourth one, integral of e to the power of x dx equal to e to the power of x plus c. This is still more easier because we know the derivative of e to the power of x is e to the power of x. So pretty straightforward. So therefore, integral of e to the power of x dx equal to e to the power of x plus c. Fifth one, a little bit trickier. Integral of a to the power of x dx equal to a to the power of x by natural log of a plus c. Now, again, let's prove this by taking the derivative of the right hand side. So let's say the integral f of x equal to a to the power of x by natural log of a plus c. Take the derivative of that. 1 by natural log of a is constant. So we take it out and take the derivative of a to the power of x. So now we manipulate a to the power of x. We take it as e to the power of natural log of a to the power of x. Since e and natural log are inverses. So x comes down because of this natural log. So we have e to the power of x, natural log of a. And now we differentiate. E to the power of anything is e to the power of the same thing. So e to the power of x, natural log of a, times the derivative of that exponent, that is natural log of a. Natural log a cancel out, and we are left with e to the power of natural log of a to the power of x. Here e and natural log cancel out, and we are left with a to the power of x, which is what was there under the integral. So as you can see, it is pretty straightforward to actually prove that a particular integral is correct or not. by just taking the derivative of the right hand side. Of course, deriving it from first principles is going to be a little bit more trickier. Okay, there are many more standard integrals. We will look at some of them in the next session and further sessions. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.